Okay, this is the fourth and last video about gravity in orbits. We learned about energy in orbits. We said the potential energy associated with gravity is gmm over r negative, where zero potential energy occurs when you are infinitely far away from everything. Now, it turns out that there is a particular energy associated with each particular orbit. And so, not surprisingly, the total energy of the orbit is the potential energy plus the kinetic energy. And we'll look at the relatively simple example of a circular orbit first. So imagine that we have a star of mass m, or a planet of mass big M with a satellite of mass little m circling around it. The radius of the orbit is r. Now, that means that the potential energy associated with this orbit is negative gmm over r, not surprising. But it turns out that there's a particular velocity that that satellite must have, and it's given by Newton's second law, that the net force, which is gmm over r squared, equals the mass of the satellite times its acceleration, which, because it's going in a circle, is v squared over r. M's cancel, one factor of r cancels, and we find that v squared is equal to gm over r. And the kinetic energy, which is 1/2 mv squared, just ends up being positive gm m over 2r. Which is kind of interesting because it means that the kinetic energy is exactly half of the negative of the potential energy. The potential energy is always negative, the kinetic energy is always positive, and the potential energy is always twice as negative as the kinetic energy is positive. That sounds weird. But the total energy is k plus u, which we find out equals 1/2 of the potential energy. So for a bound orbit, the energy will always be negative. If you have an orbit with positive energy, it means it's not a closed circle. It's going to escape to infinity. But if your orbit is going around and around and around in a circle or an ellipse, that means it is a bound orbit and the total energy will be negative. And so let's look at an example here. This is problem 61a. If you've got a satellite of mass m, we don't know the mass, so we'll call it m, and we want to get it up to 1,500 kilometers above the surface of the Earth, and then we want to put it in a circular orbit once it's up to that altitude. So the idea is that the energy required to move it up to 1,500 kilometers is the change in its potential energy, delta U, and the putting it in an orbit once it's there is its kinetic energy. So let's start with the potential energy. Now the change in the potential energy is going to be its final energy minus its initial energy, and it does have initial energy because it starts off at the surface of the Earth and not at infinity. So that's going to be gmm over rf minus gmm over re. Re we can look up in the back of the textbook, and it works out to, and it's 6.37 times 10 to the 6 meters. And the radius of the orbit is 1,500 kilometers above the surface of the Earth, so it's 1,500 kilometers plus the radius of the Earth, which works out to 7.87 times 10 to the 6 meters. If we plug these numbers in, we get g times big M times little m, all times 3 times 10 to the negative 8th inverse meters. All I've done is I've plugged these two numbers into that equation. And that's how much you need to increase its potential energy by in order to get it up to that altitude. Now the kinetic energy, it starts off with no kinetic energy, so it's just 1/2 mv squared. But remember, we can also say that that's equal to, because it's a circular orbit, negative u over 2, which is g mm over 2r, and that's the radius of the orbit, rf. And if we calculate that, it works out to be gmm times 6.35 times 10 to the negative 8th inverse meters. And so we find that K is larger than the change in potential energy by a pretty wide margin, and therefore it takes much more work to put it in orbit. If the orbit was higher, what would happen is that you would need to increase the potential energy more, but also if it were higher, the kinetic energy wouldn't have to be as high because satellites in higher orbits don't go as fast. But that is a little bit on the complicated side. 61B and C ask you about two somewhat higher orbits, and we find that for the really high orbits it takes more potential. You need to increase the potential energy more, but not the kinetic energy as much. And we've done some calculations for circular orbits. All the math that we've shown, except for the basic idea that total energy equals kinetic plus potential, is specific to circular orbits. For elliptical orbits, energy is going to be conserved because gravity is a conservative force. But the idea is that if you have an elliptical orbit, the sun's right there, if you look at 2 points on the orbit, so let's say this point here where the distance is r1 and it has speed v1, and this distance out here where it's a distance r2 away and has speed v2, the total energy will be conserved. So the sum of the kinetic and potential when it's close to the sun is equal to the sum of the kinetic and potential when it's far from the sun. And a result of this is that you can calculate the velocities, given both radii and one of the velocities anyway. So the idea is the potential energy, which is gmm over r negative plus 1/2 mv squared is equal to a constant which you can use to solve some problems. And total energy is always negative for any bound orbit, whether it's elliptical or circular. Last thing is the idea of a transfer orbit. So let's say you are planning a mission to Mars. You have the sun right here. You have the Earth in its almost circular orbit here. And you have Mars in its larger, almost circular orbit right there. Now it turns out that not the quickest, but the lowest fuel requirement way to get from Earth to Mars is that you leave from Earth right here. And you do that, once you're in orbit around the Earth, by giving yourself a burst of speed, increasing the velocity. So Earth orbits this direction. And so what you do is you speed up your spaceship, give it a little kick that way here, which will increase the energy of the orbit. And that increasing the energy of the orbit means increasing the semi-major axis of it, basically. So all of a sudden you're going to start moving farther from the sun. And if you do it just right, you end up in an elliptical orbit that is in the same place as Mars when you've gone halfway around the sun. Now at this point, if you want to go into orbit around Mars, you have to speed up again to put yourself in Mars's orbit. Otherwise, it'll just come back around like that and keep going in that elliptical orbit. So in order to prevent that, I'll erase that. What you have to do is fire the engines again, give yourself another burst of speed that way, and then you're in the same orbit as Mars. That's called a transfer orbit. Not really part of the AP curriculum, but it's still kind of cool. Now, tomorrow we'll look at question 7, and I'm also going to check problem 26. We are now done with gravity and done with mechanics. Our next unit will be the second half of the class, electrostatics, magnetism, all the fun and rather more difficult things.